Thank you for the invitation to give this talk. Unfortunately, we still meet with you virtually. I hope that we will have a chance to meet physically again next year, BPM 2021. At this stage, we should accept the situation and take good care of ourselves, our families, and our community. So here in Melbourne, we had the lockdown till September 15th, and recently it was extended to October 26th, despite the fact that the COVID-19 cases are going down here in Melbourne. So we now stay home for a very long time, and it is a good opportunity to reach out for you and have this intellectual discussion. Okay, hello everyone and welcome to my keynote. My name is Artem Polyvyanyy. I am a senior lecturer at the School of Computing and Information Systems here at the University of Melbourne. Today I would like to share with you my thoughts about business process management and artificial intelligence and where do these two disciplines meet. So the rough agenda that I plan for the next hour or so is that I will talk about one aspect that I think makes a strong link between BPM and AI. You will hear about this aspect just in a couple of minutes, so please be patient. Then I will demonstrate how this aspect is inherent to BPM and AI, and this is exactly where I think the two areas meet. Next, I will present two concrete examples of where BPM and AI fields cross-fertilize each other, which is the work that we conduct at our group here in Melbourne. Through these examples, I hope to demonstrate associated challenges, opportunities, and applications of the techniques that emerge at the intersection of BPM and AI. And finally, I will open the floor for questions and discussions. On this slide, you see two photographs of Melbourne, one taken in 1862, you see it on your left, and one taken recently, which is shown on the right side of the slide. Well, if I'm precise, the picture on the left is not a photograph, but a lithograph. Melbourne was founded on the Yarra River in 1835, so this level of development was achieved in less than 30 years, which is quite impressive. So this lithograph shows the view from the Princess Bridge. In the modern view, the Princess Bridge is the next bridge if you continue walking along the Yarra River by leaving the boundaries of the slide to the right side. So if I continue walking in this direction, then eventually I will hit the Princess Bridge. Actually, it's the next bridge along the river walk. So actually, if I'm precise, again, the modern photo of Melbourne was taken not this year, but on this day, September the 14th, 7 years ago, and I took this photograph from Wikipedia. But this is not that important in relation to the point I want to make. The point I would like to make is that in the past 1.5 centuries, we have seen a massive development of technologies and the quality of life of the humankind. The span of time between these two photos roughly corresponds to the timeline of the 4 industrial revolutions that we have experienced and are currently living in. If we look closely at the motivation of each of these 4 revolutions, we may notice a common trend. So each of these 4 revolutions suggests that it is an ongoing automation of traditional, and of course traditional at the time of observing a particular revolution. So it is an ongoing automation of traditional manufacturing and industrial practices. So in the first revolution, the automation was due to the introduction of steam power and mechanization. The second revolution is memorable for introduction of electrical power and mass production in the end of 19th and beginning of the 20th century. So a bright example of automation at that time is mass production of Ford Model T. The third and the fourth revolution increasingly promote the value of computation and data. So the role of computers in the automation of the third generation becomes paramount. So the development of cyber physical systems, sensors, networks, Internet of Things drives modern automation. So these systems, networks, and things, they're around us. They collect data and information about us and our world, our environment, and then they derive decisions and take actions based on those decisions. So note that often this is done without human intervention, and in this way they improve our lives, or at least they claim or they aim to improve our lives. All this collected data is then referred to by the term big data. I use this slide to teach my students what big data is. So a computer scientist like myself can tell you that big data is data that does not fit in main memory. A statistician would tell you that big data is data with lots of observations and features. Also, there is an opinion that big data is data that can be processed by standard statistical tools like SPSS or Excel, etc. So as you see, there are many different opinions. Some people think that it's not only about data, but also about those analysis techniques that are used to process large arrays of data. And all of these definitions and all of these claims are, of course, valid and well, contribute to the understanding what big data is. But the main idea is, of course, that given the data that is around us, that's been collected continuously around us, then there is some mechanism here in the middle, which is some form of magic, black magic, if you wish, because it's usually produced by some black box computations, produces value, right? So we can gain insights, we can infer insights from that array of data that we are processing. And then we use big data to drive automation. And you may have heard about V's of big data. According to different classification, big data is characterized by 3, 4, sometimes by 5 V's. And on this slide, I will show you how these characteristics of big data drive the automation, or at least my opinion on how this is happening. So the first V is variety. So here we refer to variety of different experiences, like, for example, products, services, processes that are offered to customers. So let's arrange these experiences on the x-axis. Naturally, we will strive to increase the variety of experiences offered on the market, as well. If you think about it, it indirectly suggests the level of development of a certain society. And the second V will be velocity, or the speed or the frequency of observing and capturing the data that relates to certain experience, right? So certain product, certain service, certain process. And we can plot velocity on the y-axis and arrange the different experiences on the x-axis according to their velocity, right? And then we gravitate those most frequent towards the left. And such a plot may form an exponential distribution. It actually may or may not. So let's assume it does. And we obtain the plot like the one you see on this slide. So the next V is value, right? So I already talked about value, so usefulness of these experiences. And then on the y-axis, we plot values which are function of velocity and value. So the experience get reshuffled from most frequent and valuable to infrequent and negligible, right? And of course, we will want to automate those that are more frequent and more valuable. So we can think of such a concept as a threshold at which we make a split of these experiences into those that are frequent and valuable, and we want to automate. We feel a pressing need to automate them now, and those for which we may postpone the automation. The next two V's are volume and veracity. So in order to achieve automation on a certain experience, we need to have a sufficient volume of data, right? In terms of gigabytes, terabytes. If you just have very little data, it just can be not enough in order to see insights, to make conclusions, to see statistical, some statistical trends in that data. So there must be simply some volume of data available. And in addition, we also need to ensure that data quality is in place. So the mapping between what we want and what we can automate doesn't really follow this sharp cut on the threshold, but it's rather blurred close to that threshold, right? So we can have something that we desperately want to automate, but we just, cannot because of the volume of data, of some of the characteristics of the data, quality, etc. Or maybe something is not really important to automate, but because we can, we do that. And last but not least, together with these 5 V properties, we should keep also one S in mind, and this is a skill. Right? So this is a skill, and if I click now here, that's reveals on the slide, and this is this S that stands here. So the V's of big data or data-driven automation. And right, so we may want to automate certain experience and even have all the required characteristics for associated available data, but we just may not have the skill, or we may just don't know how this can be done. And this skill may still need to be discovered. So I claim here strongly that modern automation is driven by data and insights we gain from data, and this is roughly the process we are following, right? And this snapshot can be refreshed in different moments in time, right? So this threshold moves, it's a dynamic concept, new experiences appear, the variety of experiences changes, something is already automated, something is not yet interesting for automation, becomes interesting at a later point in time, etc. So now let's take a look at the academic fields that are in our focus, so namely AI and BPM, and paying attention on how they promote automation. And to do that, I looked at some good books in both areas with the aim to understand how do they identify these disciplines, right? So for BPM, I looked at the book by Matthias Westke, who was my Ph.D. supervisor, and this book was also the first book to give a comprehensive definition of BPM. And the first edition of this book was written at the time I was doing my Ph.D. in Potsdam, and now it's in its second edition already. And the second book I looked at is the book by Marlon Dumas, Marcello La Rosa, Jan Mendling, and Haya Ryers. And the text that you see on the slide is the result of my attempt to synthesize definitions of main artifacts, main aims of BPM from these 2 books. So a business process is an orchestration of activities, resources, either human or computerized, of an organization. That, right, and this orchestration aims to achieve a present business objective. So here I would like to highlight this search for the balance between human and computerized resources. Clearly, one way to achieve the goals of BPM, which are concerned with improving the ways business processes are improved with the ultimate goal of reducing their costs, execution times, and failure rates, as you see on this slide, is through the delegation of human activities, which includes decision making as well, right? So activities and also doing the intellectual work of decision making to machines. So to those cyber physical systems, sensors, networks, Internet of Things networks, etc. AI is then relatively a new field in science and engineering, and it has its charm due to the nature of the problem it attempts to solve, right? And it attempts to build these intelligent entities and systems that can simulate humans and animals, mainly their natural intelligence. So to understand the state of the art in AI, I looked then in the books by Stuart Russell and Peter Norwich, and also a very interesting recent book by Melanie Mitchell. And in the later book, the author argues that we still tend to overestimate the abilities of AI, and that today's AI is far from general intelligence. I thought, well, that's interesting, because, well, when I was doing my bachelor studies, roughly, well, not yet 20, but almost 20 years ago in Kiev, that was pretty much the same perception of AI. So AI still lacks a lot of abilities. So I still fully agree with this claim in 2020. But nevertheless, of course, we should acknowledge the recent developments that are happening in AI, especially in specific, these highly focused tasks where we observe that once required data is available, modern AI techniques, modern AI algorithms, they can outperform humans, or at least keep up with the performance of humans. So this ability to outperform or keep up with human performance when accomplishing tasks and taking decisions based on data can greatly impact the balance between human and computerized resources that participate in business processes, about which I talked on the previous slide. So if BPM and AI would truly meet, they will clearly both benefit. The benefits for BPM are, in my opinion, immediate, and therefore, well, almost obvious. They stem from this automation of specialized activities and decisions. So, for instance, at the bottom of this slide, you see an example business process diagram, and in this diagram, certain activities, certain decisions are marked with, well, as a manual activities, manual decisions. And so these activities and decisions are then candidates for using AI techniques to automate them. So for instance, the decision to take a thorough or a casual, simple check, right, can be done based on some neural network, some convolutional neural network, which is trained on the data, and somebody is drawing on the slide. Thank you for that. Right. So based on some neural network that is trained on the appropriate data to carry out those decisions. So similar, like here on this slide, you see the network is trained to classify photos of cats and, well, or other photos to identify if that is a cat or not a cat. So those specialized activities, right? There can be chatbots, for example. There's a lot of, oh, sorry, I'm pointing to the wrong screen here. So chatbot, or computer vision, or speech recognition, or speech generation. Those would be those specialized tasks that are not the general intelligence, that don't require general intelligence, and assuming also that you develop those chatbots, those speech recognition tools for a special domain in BPM or some business process that becomes even further specialized. And then, well, AI in its current state can cope with those challenges and derive the value for the business process management. All right, so if I would think about benefits that BPM can bring to AI, well, maybe it's probably not that immediate, but still I think there is something that can be transferred. So for example, we can use data-driven techniques from BPM, mainly proposed in the area of process mining, to learn those artifacts based on which then decisions are automated or semi-automated. So we can discover process models from data, we can do conformance checking to align reality and designed models, measure the quality of this model. So in that sense, we are contributing to explainable AI, because we are creating artifacts from data which are explainable. So in process mining, we would strive to build models like this one in the bottom left to explain what is happening. And those are, of course, inherently explainable to business analysts. And that's how we can build these artifacts. We can understand, we can then reason and think if we can trust them, if this is the ethical way of doing things, etc. So they can, if not maybe open completely, but give us a peek into this black box of AI, right? So not that black box where you get the input, the magic, this black magic happens inside of that black box, and then we get the output. So that's where I see that BPM can contribute the most to the area of AI at its current state of the art. All right. And just to emphasize process mining, because I told you that process mining is this data-driven area of BPM, right? So in process mining, the main data artifact is event log, which is a collection of events that are generated by IT systems, software systems that well support business processes. Sorry, so support business processes in organizations. And okay, I just can hear some background noise. Okay, it's gone. So we generate event logs based on IT systems that support business processes at organizations. And then, so this is a sample event log. We can think of many attributes that we collect for different events that are stored in event logs, but usually we require that events have at least 3 attributes, so case ID, timestamp, and activity, so business activity that happened, and then we will translate them in this cases or traces, right? So blue trace, which is also here denoted by blue rows, green case, which is denoted by green rows, and the reddish kind of case. And then this is our traces, and we will try to learn the models which have the structure which actually refer to the business activities that were happened that are highly explainable. We will also try to understand the conformance of how well that model represents what was happening in reality and captured in the event log. So this is what we do in process mining, learning some insights from the data. And this area is heavily developed and driven by Professor Will van der Waals, who currently works in Aachen, which is in Germany. All right, so this was my introduction, so where BPM and AI can actually meet. And now I want to talk about 2 concrete examples of research in this intersection of BPM and AI that I was also involved in. And the first is on automated goal recognition. So goal recognition is a classical problem in AI, and what I will show to you is how we tackle this problem using techniques from process mining, right? So goal recognition consists in automatically detecting the goal an agent attempts to achieve. So for the first time, I was exposed to this problem in April 2018 when I attended a talk by a person from the Australian Air Force that took place at our school here in Melbourne. And this talk was about simulator of aircrafts and decision-making component of this simulation that should support pilots that need to recognize the goal the other aircrafts around are trying to achieve, right? And so these suggestions of what others are trying to achieve, then the pilot should be able to make a decision how that he himself should act in that situation. Should he attack? Should he continue patrolling the area, go away, etc., etc. So this is the problem. And of course, there are a lot of also peaceful applications to this problem, right? So let me just maybe introduce this problem in a more peaceful setting. So think of a grid where you have, well, cells, and you can walk in this grid, and there is a starting point, this initial point here denoted by capital I, and there are some goal cells, A, B, C, D, E, F, so there are 6 goals in our world, and you see two sample walks from initial state towards goal E, right? And the red one would be like a rational walk, right? So we first deviate from the trajectory towards our goal, and then we kind of go back to the trajectory towards our goal. And the green one is more or less rational behavior towards the goal. And what we do, right? So then we kind of should take these observations, put them in this black magic box, do some magic around, and we need to infer the probabilities of goals. So, right, so which goal is the most likely goal, and then accept that the most likely goal is actually the goal the agent is trying to achieve, right? So here you see that after each step we reshuffle, we recompute the probabilities, and for the rational walk, which is a green walk, well, at some stage the goal E starts to win clearly, right? And that's basically keeps like that towards the very end of the walk. And for the rational walk, well, what we do, we first start and we think that the agent is going towards goal C, right? The green goal is goal C over here, and right. So these are first 5, 6 steps. So somewhere the agent is here, and we are thinking that that agent is going towards goal C, and then when we start to go into the right, slightly the probability of goal C declines, and the probability of goal E, the actual goal the agent achieves at the end, starts to rise and actually is shown to be there. So this is a general problem, and well, when we try to solve that problem, so first what we did, we looked at observational learning, and observational learning is learning that occurs through observing the behavior of others. So according to Bandura, and his social cognitive learning theory, there are 4 phases that influence observational learning, and these are attention, retention, motivation, and production. So you may have seen this video online where mother duck goes on the stairs, and then the little ducklings try to follow the mommy duck, right? So they observed, they paid their attention of what their mom has done, they retained that behavior in their memory, they were motivated to recreate this, repeat that behavior, so they were producing that behavior, so failing at the start, but eventually reaching their goal, right? And this type of learning is actually doesn't need reinforcement in many cases. So we took these 4 phases as the general framework and kind of conceptualized it a bit further and developed this framework, which we published earlier this year. It's a framework for goal recognition, which is inspired by this principle of observational learning. It was published in AMS 2020 conference. And basically, right, so this framework is composed of these 4 phases: attention, retention, motivation. But instead of production, we are not really repeating the behavior. We are just recognizing the behavior of others based on what we learned. And each of these phases then has certain workflows, right, that, well, recreate the behavior that should take place in that phase. So this framework is defined from the point of view of some intelligent agent that observes and learns from agents around, and later, when the learning has happened, that agent is able to take decisions about which goals the observed agent is trying to achieve, right? So for example, what we need to do, well, during the attention phase, we need to capture those actions that we observe by, for example, by agent A, we observe action S, by agent B, we observe action B is done. And also we need to be able to recognize that there is some goal completion. So for example, agent A has achieved goal alpha, etc. And then in that retention phase, we will capture that action, we will append it to the trace, to the current execution trace of agent B or agent A, depending on which agent we are currently observing. And at some stage, we will observe that the goal is achieved. We will retain that trace into the skill library, and then we can learn the model, which we call a skill model from this data, and that will be our knowledge about how certain goals can be achieved. And then at the motivation phase, the agent decides, okay, now I want to recognize certain goal, and if that decision is happening, well, we are appealing to our retained memory of what has happened. We then kind of check conformance of what we know about the skills to achieve different goals and what we observe currently, and then we infer our goals. So basically, we then instantiated this framework with process mining techniques, right? So we observed many trajectories towards different goals in our grid, and we learn a skill model, like a Petri net, using the process discovery techniques from process mining, which captures the behavior towards a certain goal. I think this one captures towards goal A, the behavior towards goal A. And then once we observe a new trace, and once we observe a new behavior in our environment, we do conformance. We kind of say, where are the skills and the observations deviate, where they coincide, and based on this knowledge, we then propose a mathematical model that allows us to derive this probability distribution. So this was the paper published at AMS conference, as I told you, called Goal Recognition Using Off-the-Shelf Process Mining Techniques. So we were just taking available techniques and composing Z solutions and testing how good that solution can perform. That was basically the idea of that paper. If I can just go quickly through the steps. So we take the observations, we compose event logs. So for each observations towards certain goals, for example, all the blue arrows, all the blue walks towards goal A gets collected in the event log for that goal A. All the dark red walks get collected in event log B, etc. And note here that we don't actually need to know information about the environment we operate in. So this is also very different from available techniques in goal recognitions, which will often require the full knowledge. Here we just observe, and what we observe we know, right? So that's a very different aspect that we have in our approach. Then we take event log, for example, for goal A, and we construct a process model, the skill model of how to achieve that goal. Right, so it's actually, if you look closely at it, you understand that this is highly explainable. So right, so from the initial state, we can either go north, so we have here an arrow, or we can go north, west in this case, etc. So we kind of can explain what is happening based on this model. This one was constructed using split miner, developed by Adriano Augusto, who is also a member of our group, but also in the evaluation we used transition system miner, developed by Eric Verbeek in Eindhoven. So we learned the skill models, and then when we observe this new fragment, new behavior, we perform the conformance checking. We construct such conformance diagnostic between the currently observed trace and the skill model. Actually, we do that for each of the skill model to assess them to which of the skill models the current observations align the most. Right? So here, if I explain this artifact a bit more, so the top two rows of this table, they correspond to observed actions. So right, so the agent was going north, north, west, northwest, and north, north again. Right, so this is where the agent was going north, northwest, northwest, north, north. So these are the observations of the agent, and this is what model can support. So in the model, I can also go north, northwest, northwest, but then I cannot continue to mimic the behavior of the agent. So now the observations and the skills that we know deviate. So and the best explainable correspondence between observations and the skills is that the model needs to continue by going northwest 3 more times. So if I go back to the model, where is that? It's here. So the model can do north, northwest, but then I can just complete the whole execution by going northwest. Well, actually, sorry, I go north, northwest once again, and this is exactly what agent is doing, observed agent is doing, but then the model needs to continue by going northwest, northwest, northwest 3 times, and then kind of we're reaching the goal. So this artifact, it's a technique is called optimal alignments, a well-known technique in process mining. We can compute the smallest deviations between observations and the skills, and then, right, so we can also have some costs on different steps. So for example, the bad move costs us something. For example, the move to the north costs us $1 Australian, and diagonal move then costs us the square root of 2, right? If we assume that the going north, west, east costs us $1, then the diagonal move will be a square root of $2, which is 1.41 cents. Etc. We can search for such optimal alignments, so alignments which have the smallest cost. And then we use these alignments to compute the weights, and these weights, they are kind of another layer of abstractions that now have the logic of explaining the likelihood that the agent is trying to achieve certain goals. So basically it's a scary formula. I'll not go into depth into here, but there are 4 parameters we try to control here. So phi will be some constant which smoothens the likelihood, right? So if we will start with 0, let's say weight, and from initial state the agent takes some move, and let's say it takes a move according to one skill towards one goal, but deviates from all others. So then basically the difference between that goal and all others becomes kind of infinity, 0 and something. So we need to smoothen that, and that's the factor phi rho. Also, we penalize asynchronous suffix. So these moves that are asynchronous at the end, we say that they should be penalized more because, well, if at the end the agent deviates from the goal and is persistent in that deviation, it's most likely that the agent wants to go away from that goal, and these parameters lambda and m, they allow us to control that, etc., etc. So there are these factors. I'll not go in details in all of them. So basically also, right, so this I is then the number of the number of the step we are observing, and the later we are in the trace, the more weight we give to that step. So if it's aligned or misaligned, if it's misaligned step and it's already the step number 10, already long way through the walk, well, that's more costly deviation, right? So from the goal, etc. So here are some examples. So right, so if I compute alignment weight for the first 3 steps, which are completely aligned, and for these parameters, so phi of 50, well, there will be 50. Everything else is aligned. The weight of that trajectory is 50. But then if I compute my weight for this complete trace of 5 steps, then, well, I'll have my 50 cost, which is a smoothing factor. But then we also have 2 steps at the end which misalign, and also will penalize some deviations here. So 4th and 5th steps deviated, so there'll be some weight of 52.8. Well, think of this just as numbers which encode somehow that logic of where we want to put the emphasis on corresponding or misaligned moves. And then we given these alignment weights, which we compute for each of the skill models, for each of the goals. We then use Boltzmann distribution to derive distribution over all the goals, right? So the probability of a goal given the observation tau, this is a trace we observe, is computed according to the Boltzmann distribution. Well, why? Well, basically because my colleagues who are experts in goal recognition suggest that this is state-of-the-art way of doing this in AI area for recognizing the goal, and also it allows us to use this parameter bit beta over here, which is like a temperature that controls the level of confidence of the goal recognition we are doing. So it can also be interpreted as a trust over the learned models that we constructed from the data. So we obtain this probability distribution, and then goal C here is the winning goal. So we suggest that probably at that stage, at 5 steps through the walk, the agent, so my mouse keeps disappearing, the agent is most likely is walking towards goal C. We did some evaluation with real data, with the community from BPM and process mining will be very well aware about this data. We looked at daily activities of daily living. This log was made available in one of the papers, right? And also we had the logs for Dutch municipalities for doing the building permits and environmental permits. So that those logs contain business processes of 5 municipalities in the Netherlands and how they were basically handling different processes in those municipalities. So by observing certain fragments of those logs, we were trying to guess, to predict towards which municipality that goal is now taking place, so in which municipality that business process is now executed. And also we did some synthetic evaluations using planning domains from AI, from navigation, so walking in the grid as I showed to you, and also blocks world, where you have basically a pile of blocks and you want to reach some configuration of those piles, and there are some rules where you basically understand how you can move the blocks, how you can lift them, where you can put them, etc., to achieve your desired configuration. So we took the constraints of those worlds, basically those constraints completely describe the world, and we simulated some sample traces and use those traces as potential observations, like observations of behavior, and we learn skill models, and then using new observations we are trying to recognize the goals. So for the real life domains, we then we just understood that we are performing better. We actually didn't have a baseline to compare with. Well, our recognized goals are doing better than the random guess, so to say. So precision recall is much better than random guess. If talking about planning domains, we also did some different configurations of our worlds. So let's say we had different number of goals, different grid sizes, trace optimality for learning or for training and testing the goal recognition, observed percentage. So we were observing partial traces, not the full trace, but let's say 50% of steps in the trace, number of training traces that we used, etc. And then what we observed that right with a different behavior of the factors. So if we increase the number of goals, if the number of goals go up, then performance goes down, right? In the world, the more goals we have in that world, well, the more congested the walks in that world is, and the harder it is to discriminate between different goals. But if we increase the grid size, for example, then we, well, the walks become more sparse, it's easier to do goal recognition, so performance goes up. The more optimal are the traces, the less they deviate from the optimal trajectory, the better the performance. The higher the percentage of observations, the better the performance. The more the training we do, the better the performance. So these are the kind of observations we had. We compared with some techniques in goal recognition that use planning and the knowledge of full world. We often observe that we are faster in performance to do goal recognition, but also lower in recall, as our approach doesn't rely on full knowledge of the world, right? So there are some pros and cons, and currently we are working further in doing the comparisons and trying to understand how can we tune the parameters of our model, and when one parameter is more important in which situation it leads to better results, right? So the paper was written together with my colleague Nir Lipovetsky here at Melbourne, who actually working on planning. with Sebastian Sardina from RMIT University, also here in Melbourne, and also with Zihan Su, who is a student, and he recently started a PhD on this topic, so we hope to continue with this line of research. All right, so this was one application area, and I would also like to demonstrate you another application area, which is robotic process mining. Recently, it is also referred to as task mining. Basically, Gartner is advertising this term very strongly. Well, I know I have a lot of physical robots on this slide, but it is actually about software robots that I want to talk about. So robotic process mining aims to automate, it aims to automate robotic process automation. That's the very correct way of putting it. So RPA automates, robotic process automation automates repetitive clerical work by executing scripts, or also called RPA bots. So what can be that repetitive clerical work? For example, transferring data from one system to another, from Excel form to a web form. And actually, this is not fiction. This really happens in life. We also observed this in University of Melbourne. Our enrollment team does a lot of this manual work on transferring data from Excel forms into our systems, and then there is also the RPA team that helps them to automate these routines that they are doing. Right, so here you see this form in Excel with student information, and then you need to transfer this information into the web form, and then click submit, and then this information is stored in the information system. And so how it's done at this moment, so how do we do RPA now? There are solutions, there is big industry behind this. So what is suggested is that we observe interactions of users with information systems. So basically we observe what is clicked, what is copied, where it is pasted, which button is clicked in the UI. So, and through these observations, we kind of identify routines, and then we code those routines into the RPA scripts. So little programs, little scripts that now do this data manipulations in the information systems in the UI automatically. Right, so this is, of course, is a very error prone. We should do it offline, kind of difficult to maintain, mainly because of a big lag between observations, acquiring these observations, and coding, and then actually putting this into practice. And this is it can be quite a lengthy process. You can be very late with your RPA script because already, well, the format of data changed, etc. So what we propose is to forget about this manual, mostly manual observations of how work is done, and record automatically what is happening into so-called UI logs, and then use those UI logs to identify routines automatically. And once we identify those routines automatically, we also don't code them manually, but we discover models, then later we compile into those executable RPA scripts. So this is our idea, our vision for automated robotic process automation, right, so that's our term, robotic process mining. This is basically the picture of robotic process mining, and it is data driven. You can do it online, you can do it just as you go, as you click in your system, and then the system can automatically suggest you, look, you are repeating this very often, do you want to automate that? It's very flexible because if your work practices change, if kind of data format changes, you can quickly readapt, etc. We have a team behind this, so it's not me alone who working on this. So we have a PhD student, Volodymyr Leno, who drives this line of research. Also, we supervise Volodymyr with Marcello La Rosa here in Melbourne. and also there are two external supervisors, Marlon Dumas and Fabrizio Maria Maggi. And the first paper we published on this topic was Robotic Process Mining, Vision and Challenges, published in Business Information Systems Engineering Journal. And in that paper, in that article, we summarized the pipeline of how to get from those observations that are happening, inherently happening in the real world, to the RPA scripts. And basically, this is a pipeline of different problems that need to be solved. And once you solve this problem along the pipeline, you derive at an RPA script. So you start with recording what you observe, then you segment it into the traces, because, well, you record a continuous trace, right? So you don't have this notion of start and end of a business process. You really record, let's say, a session of work in the course of a day, and then you need to segment that, then you need to simplify, you throw out some non-value added step, then you identify candidate routines that you think what is executable, then you compile, and then you derive an RPA script. So we also have tool support. So first we worked on the action logger to record those UI logs at the level of abstraction of actions that we can then later take forward and automate. And we published that tool and discussed that tool in the paper at the BPM conference at the demo session last year. It's called Action Logger. And this year, I think on Wednesday, Volodymyr will present Probidium, a tool which then supports all the subsequent phases and implements the results of our theoretical work on how to solve these different steps of this pipeline. And these are the theoretical results of a lot of publications on different steps. The most techniques we were developing to discover this executable routines or subroutines. So you see this very intensive. There are 3 papers here listed, but kind of we now achieved the first coverage of the whole pipeline. So this is the UI logs we record. I'll just say few words about some of the steps of this pipeline. So in addition to those 3 usual suspects of the events in the event log, so case, actually there is no case ID here. So in addition to timestamp and action, right? So we will not have case ID, and because this is a continuous trace, and also there will be a different payload of other attributes that we believe are important. So let's say which cell in the worksheet was clicked, what was the field value, etc. So there are additional attributes which you need to collect in order to then support the use case of RPA. And that's what our tool action logger is doing. It collects that UI logs, it records those UI logs. Then this year at ICPM conference in October, Volodymyr will present our work on segmentation. So once we now have this continuous trace, we need to cut it, we need to segment it into these small chunks, small exercises of transferring information for one student from Excel form into the web form. And what we do, just in a nutshell, we construct the directly follows graphs, where vertices are actions and edges are the immediate follows relationships between the actions that we observed. And then we identify strongly connected components, right? So those strongly connected components denote repetitive behaviors, and then through the dominator tree, so the entrance to the strongly connected components and the back edge, which tells us, okay, you return to the same behavior again, we then segment this continuous trace into multiple smaller segments. And well, to learn more about this, I would suggest you to follow the presentation of Volodymyr later in October. So then also we need to automate a lot of data transformation. So for example, this is a snippet of this UI log. I showed you several slides before. And here you see that, well, we manipulate the phone number, right? We copy it, we paste it, and also then we edit it already in the web form. We edit it, and we remove the country code. We replace space characters with dashes, with minus characters, etc. So how do we automate this, right? If we have one format of data as input and the other format of data as output, we also had a paper on that. So basically, we look at the whole task of transferring the data as a big transformation, where for certain fields we will do the joining of the data elements, right? So for example, here we concatenate first name and last name. Sometimes, I don't see where, sometimes we will split the data. For example, address will get split across multiple fields in the web form. Sometimes we will actually copy, paste, and edit the information as shown here in the in this field of the web form. So how can we actually automate all of that? And for that, we looked at existing techniques that aim at automation of such data transformations. So basically what we do, we take the whole input and output as two big chunks of data. And right, so they are, of course, in different formats. They can be split, joined together, different transformations can be happening. And then we are trying to discover the transformations from input to output. And we use, well, the approaches, techniques from program synthesis, which basically composes that trajectory from input to output of operations that you need to perform in order to get the transformation right. As of here, we need to split the input, the form, based on the space character. So we need to want to do this based on the first space character. So we have the country code separate from the rest. And then we need to drop the element 0 to get the output. So this is one way of achieving the output from the input. Other way is that we split the input based on space. So we do the big splitting of all the parts. We drop the country code, element 0, and then we join once. So joining the first and second column, and then joining the two remaining columns and arriving at the output. And so there are multiple ways. So there's kind of a search that is happening here, and then we select the one that requires least number of steps. That's our then transformations that we are then automating into a script. And of course, so this is very nice, very simple, but also we have two optimizations, because in general that can run forever because the search space is quite big. So in the paper that I showed, that I listed on the previous slide, somewhere on the previous slide over here, in this paper, which we presented this year, believe me or not, in New York in February, we were still there physically, and then the lockdown started to well, happen across the world. So in that paper, we presented two optimizations. How can we use domain knowledge about the data in order to speed up the computations? And actually, the results that we obtained were quite good. So we were able to construct this transformation really, really fast, or sufficiently fast for our purposes. And then we automate the script. So in the video tool that will be presented, I think on Wednesday, if Vladimir is here, he can maybe correct me. So in the demo session, we then also generate the executable scripts. So currently the tool generates scripts for UiPath, which is a product for RPA. And those scripts can be executed and we can carry out those scripts automatically. So this is basically my last slide. This is what we do on the side of RPA. It's an area which was researched in business process management, recently got attention from AI community. So the papers that we presented in New York was presented at IPA, Intelligent Process Automation workshop. So first workshop that happened collocated with AI conference. And also I know that there is RPA forum at BPM this year, and one of the papers, I think that was accepted there, also talks about the kind of results of that workshop and some insights that were gained in that workshop in New York. All right, and this is really the last slide that I have. I listed some challenges and opportunities. I think there are a lot of opportunities to automate. automate. So the challenge is to automate these mid and highly intellectual activities and decisions. Another challenge is to identify data suitable for automation. So do we have enough data from which we can learn inside? Do we have too much data which harms our automation? We can learn a lot from BPM for doing explainable, ethical, trusting AI. We can also learn from process mining and quality measures that are developed in process mining to understand if the models we are constructing, both in BPM and AI, if they give us good generalization, or at least reuse the principles from process mining to do that. So through quality measures that are offered in process mining, but also other quality measures can be a big challenge to define and propose those quality measures that can assess how good the derived artifacts are. Also, forecasting business processes using AI is a very hot topic. A lot of work is done, but I believe also this area requires much more attention. Okay, I was not following the time, but this is the end of my talk. This is what I was planning to say, and I think I roughly used 1 hour to do that, so that's very good. So thank you for your attention, and if you have questions, I'm happy to answer them.
Thanks, Artem. You have been perfect with the time. Yes, it's time for questions. So to ask questions, I invite the audience all to write your name in the chat so I can unmute you. And you ask question real time to Artem, or to raise your hand in Zoom. So I can mute you as well. Let's see if we have questions. I can start with one question because I have one, since I'm, as you know, I'm working with a PhD student of mine on RPA as well. So I'm very interested in the topic of the data transformation. My question is, how can you map the input that have similar behavior to then map them? So I can identify this input with similar behavior and then apply the data transformation just to that input.
So how, well, I'm not sure I understood the question. I'll try to answer. So, right, so because we do the segmentation, that's a way of understanding the similar behavior. So we have this continuous trace, and then we cut it into these segments, which expose the same behavior. And we assume that within that same behavior, which is a segment, we roughly do a same automation, so same data transformation, right? So that's how we narrow down the scope where the inputs and outputs are. So then the inputs and outputs happen within the same segment, right? So then we can, through our UI logger, we can observe all the actions that took place, and some of them are copies, so read operations, some of the paste, write operations, and then we can kind of construct the problem of doing the data transformation. And so using all those components, segmentation, and then observing what is actually happening inside of each of the segments, we are composing a lot of instances of transformations, and then based on these instances of transformations, we learn the model of the transformation that happens.
Okay, okay, it's quite clear. So I have to answer, by the way.
I invite you to, thank you. Yeah.
Other questions? Oh, there is Matthias. Okay, please.
Thanks. Yeah, Artem, thanks very much. Very interesting presentation, as always, I have to say. I have a question on the RPA mining part. So it seems that you are looking at the log that is being produced. And I was wondering, because often it's the case that I work in a process, I start with one activity, I do certain things, then I'm jumping to another process instance, I do other things for that instance, and then at some later point I come back to the first instance again. So are there thoughts about investigating these types of overarching process? Because now you're looking basically at one activity and you look at the internal process of that activity. So how about this larger scope of RPA?
Thank you for the question. Very good question. Yeah, we are continuously thinking about this. And of course, right, when it's just one task, I just transfer data from web form to from Excel form to a web form. That's straightforward. And you expect to see one type of behavior inside. So, but also, if you have a larger scope, I think what helps there is statistics. Statistics helps you to identify the different frequent fragments or repetitive behaviors. So, right, it is routine, right? It is routine we are looking for. Routine is something you do over and over again, right? So I have, let's say, 50 students to transfer, and through that repetition, I should be able to see that, and maybe not all of the 50, but 47, I did exactly the same thing because it's actually convenient for me. And if I'm just very creative in that, well, too bad for the user. I don't identify the repetition, and I am not able to then automate that, right? So then we will wait for the next day when the user will be maybe not that creative or follow the same trend, and the activities will be packed into one chunk of time. But also, if you kind of switch, also we hope that the switch is not happening often, and you can see some statistical trends that now I am doing, let's say, transferring of data from Excel into web forms for student enrollments, and now I am in my head of coordinating IT students here in Melbourne, and I'm answering some emails which are of similar patterns, a similar template. I can just automate maybe even that activity. Right, so I'll again have a chunk of time where I'll be persistent in that activity of doing the task of answering emails. Mm-hmm. And if I try to segment this now long recording which contains both, well, if I construct this directly follows graph, maybe these two behaviors are now encoded in two different strongly connected components. Well, they probably should, right? And I can, to some extent, identify them. It's not guaranteed. We haven't really experimented a lot of them, but it's a very interesting problem to look at.
Okay. Thanks, Adam. Thanks.
Okay. Okay, so I have, so I'm unmuting Bernardo Nugro that he has a question for you.
Oh, hello.
Hello, yes.
Can you hear my voice?
Yeah, I hear you very well.
Yeah, okay, thank you for your presentation. So I saw one of your slides mentioning about the NLP and BPM. So is there any additional insight? What's the relationship between the NLP and BPM?
Between NLP and BPM, well, I was mainly on that slide, well, slide number 8, I think, or something. Anyway, I'll not search for it. So there are a lot of problems that AI tries to solve, right? And they are often very specialized. And that I'm not sure if I had NLP exactly. I was more thinking about speech recognition, speech generation, this type of things that can be reused in the business process management, right? Where I can, for example, make an automated call and read some information to the customer, so I don't need a human being involved. And so these things, natural language processing, well, probably there are some business processes that benefit from it. I don't have it immediately in my mind. I think on the slide I had speech recognition, speech generation. But probably there are some possibilities to do translation of text using NLP techniques, right? It's very active recently. Very active research in AI, especially, right, in the AI area. We had here several talks recently on Melbourne, giving some interesting insights into that problem. But yeah, let's say language translation. I need to translate a text as a human step, manual step. I can now automate it using NLP technique to some extent, to some reasonable quality level.
I see. Okay, thank you. Thank you very much.
Thank you for the question.
Okay, next question by also Joseph Carmona. So, Joseph, if you're there, you can ask.
Can you hear me?
Yeah.
Yes, Joseph, I hear you very well.
Thank you very much, Artem, for this nice presentation. This is a very nice overview, and I think it was at some point very technical, which was helpful, at least for me. So thank you very much. I have a question on the especially on the goal recognition. A couple of questions there. So the first one is, as you said, the conclusion that you had is that you are better on performance with respect to the other techniques on goal recognition, but you lack a bit the context in a way. So you don't have. So I was wondering whether so moving to multi-perspective process model and therefore multi-perspective conformance checking can help you to get closer on that direction. That is one question, and the other question was on the models that the goal models you extract. You have many label splitting there, so you have very few labels like going up, going down, and then you have them scattered along the model. And I had a question there. So if there is a particular goal in order to split labels with the technique you have used to discover the process model, so that you control a bit. I guess if you said that you were using the transition system miner, so I guess you want something which is very fitting the trajectories you have observed. So if you can say a few more words on how you control the label splitting in these discovered process models. So thanks a lot.
Thank you, Joseph. I'll start from the second question. I'm not sure what you mean by label splitting, right? So we had very clear steps, right? So going up, so very clear operations. I mean, the problem of actually recognizing the actions in the environment was kind of left out. We were assuming we know the actions that are happening, the move up, move left, move north, west, etc. And we were aiming not really necessarily for fitting models. We were actually hoping that we will be gaining something from generalization. Right? So that this discovery techniques that we'll be using will generalize the data, and then we will be able to kind of get the benefit of that generalization. Actually, this was our hope.
Okay.
To some extent, we observed that. I can't say that we kind of were successful in doing that, but we observed that. Also, but also one lesson, what we learned is that so these data sets that we had for working in this grid, they were quite complex and quite well. They put a lot of challenges for the state-of-the-art discovery techniques. So we played with inductive miner, with split miner, we played with transition system miner, and sometimes we observed that we were actually not benefiting from using inductive miner because at some stage we were starting to get too much of generalization. And so it was because if we had a lot of traces which had a lot of variability, like in the case of a walk which is not really going close to the optimal path, but deviates from it about 30% far, you can already have a lot of variability there, 30% from optimal, you very quickly generalize too much, right? And you basically get the almost a flower model, right, with all possible traces accepted. Probably this is because the goal is to explain this to the business analyst, so you don't want to create a big model. For us, it's good if you can explain, but if you can just learn it in a good way, so you get a useful model and you will never read it, you just keep it in memory as a skill model, you don't need to read it every day, so to say, or discuss it with your colleagues. So a bit that we were missing. So we observed generalization, but sometimes it was too much of generalization. Fitness, yes, we were going also for fitness, but haven't had a problem with that, I would say. So split minor was sometimes slow on big data sets we experienced. So transition system minor actually that we used was the best fit. That's why we use it for the evaluation at the end, for the full evaluation. But again, this is maybe the particularities of the data set that we were using. And the first question, sorry, I forgot. What was that first question?
About using multi-perspective discovery and conformance, so that you can cover also the part that you are currently missing.
So the more information we can get from data, the better. So multi-perspective data perspective extremely important. So recently we started working on stochastic process mining. I think this is a crime not to, well, to use frequencies of observations that we have in the event log, construct models based on frequencies, but then take them and throw them in a garbage bin and just have a control flow model. This is just a crime. I mean, we have this data readily available, it's valuable data. We used it in construction of the process model, and then we kind of said, yeah, this is a model, but now, I don't know, was the decision going right or left 99% versus 1% or 50-50? I forget about this. This is, I don't understand why we are doing that. I think we should try to keep as much information, which we believe is correct information, in the model. So likelihoods, probabilities, but also data decisions, if we can learn them, we should keep them. Because that will, then will be more correct representation of reality.
Thanks.
Yeah. Thank you, Joseph.
Okay, thank you, Joseph. We have time for a very last question before the break. The question is from Ahmed Awad. Ahmed, if you are there, you can ask the question directly to Artem.
Yeah, thank you. Can you hear me?
Yes, Ahmed, I can hear you.
Yeah, how are you? Thank you very much, Artem, for this interesting talk. Actually, my question is motivated by your first few slides about big data and how they can guide or motivate what to make and what to not. And I would just want to think about how these challenges or these landscapes, if you have experienced some limitations with your experiments with these big data sets with currently available tools, or how you see that what would need to be developed or what need to be tackled in this area to cope with these large sizes of big data sets. Thank you.
Yeah, so thank you, Ahmed. Thank you very much for this question. It was very bad connection. I think I just managed to grasp some of the
Artem, sorry, you should, the question is also on the chat. You can see it.
Okay. I just don't see the chat. I see.
No, the question is, how do you see the 5S of big data affecting the process mining tools landscape?
Yeah. So okay. So yes, this was the thinking of. So so of course we observed that, right? So even with this experiment that I currently show on the slide, right? So if we had very little data, so volume was not enough, performance was bad, right? We need to increase the volume. If we had, let's say, also observed percentage of observation was low, we also had a performance drop. If we had too much data, like I talked to this, the last slide, I had this bullet point, so you need to, like, the data that fits the purpose. You don't need extra data. If we had too much data, we were getting flower models, so we were losing the usefulness of models. We were generalizing too much. So there must be this balance, and you need to search, and the challenge is to search for that balance. So yeah, we definitely observed all kind of the interplay between characteristics, these different characteristics of data that I discussed, this 5 V's: volume, veracity, variability, value, etc. Maybe not all of them, because some aspects we are not modifying, we were not changing. Like, for example, the trust and data quality, we're assuming data is good, of good quality. Right? So we're not experimenting with that one. But it's a good idea to do such experiments.